Okay, so I think we can start. So for the last 4 lectures, we are discussing about Gaussian process. And the idea today is to wrap up our discussion on Gaussian process. To start with, what are the things we have discussed about Gaussian process till now? First, it's a distribution over function. Second, it's a collection of random variable, potentially infinite, any finite subset of which follows a consistent Gaussian distribution. These two things we have discussed. Then we talked about how you can use Gaussian process for regression or Kriging, same name. And there we saw that it's a non-parametric model, which means you don't parameterize your function. Instead, what you try to do is you try to impose a prior on the function itself. And by imposing the prior on the function, you try to find out the hyperparameters of the Gaussian process, right? And that is basically training the Gaussian process. This is the this is the point until which we discussed in the last lecture. However, finding the hyperparameters is actually not that important. What is even more important is to now use that to make prediction, because we are interested in building a surrogate model using Gaussian process. So that is kind of the idea. And that prediction part is what we are going to discuss today and wrap up our discussion on Gaussian process. And following that, tomorrow the idea is to wrap up our discussion on surrogate model, which means from next week we will start discussing on system reliability, time dependent reliability, reliability based design optimization, all of those things, which I will do first. I have not yet decided, but out of these three, something will start. Okay. With that background, or with that recap, more or less, let us quickly go through the steps of Gaussian process that we have done till now. That is the training algorithm, and from there we'll proceed with making prediction. Okay. So let us start. So we are talking about GP, where GP stands for Gaussian process, or to be more specific, we are talking about GPR, which is the Gaussian process regression. The whole idea starts with this, where T is the target function. Although you will not know the target function, you will have samples of the target. Y is the function, the unknown function that you want to kind of learn, I will say. Epsilon is the noise, the process noise, or the model discrepancy. And this you can model as zero mean, beta inverse. Okay, where beta inverse is your sigma y, right? Nothing new. We already discussed this last time. From here, what is the next step? We find out the likelihood, right? So the next step was that we will find out the likelihood, the data likelihood, which is probability of T given y. Why I am writing T and a bar? Because this likelihood for the data, although T is a function, y is a function, I have measurements at some finite location, let's say n number of points. So T bar at the below denotes a vector T, which is of dimension n cross 1. And what is the distribution? We know that from last lecture, last to last lecture, that it will be, mean will be y bar, and the variance or the covariance will be beta inverse I n, right? Y bar is my mean, this is my covariance. We cannot work with this, we cannot maximize this because y is unknown. So what we do is we assign a prior on y, and we go the Bayesian route of doing things, and that's what we do. So this was the likelihood. So the next step is prior, and this is all recap from last time. So prior you assign on y, so which is a GP, 0 mean, covariance kernel x, comma x dash, comma semicolon theta k, where theta k is your hyperparameter, which includes length scale parameter, process variance, both of those, right? Now this prior is over the unknown function y. GP is a distribution over function. So this prior is over an unknown function y. But we cannot work with this in the function space because t is only known at some finite number of points. So what we do? We use the definition of Gaussian process to define a prior over y bar, or I mean the vector y. So this will give me probability of y vector, and this will be, from the definition of Gaussian process, this will be Gaussian with mean 0, which is a vector of zeros, by the way, n cross 1, assuming n data point, and covariance matrix, not a kernel now, Kn. And Kn is actually not known to you because theta k is not known to you. So Kn is in terms of theta k. It's not that Kn is known to you. Kn is unknown to you. Because theta k is unknown to you, and theta k is something we need to compute. So this is my prior. From there, we go to the marginal likelihood. And still we are in the last lecture. Marginal likelihood. What is the marginal likelihood? Probability of t, the data you have observed, which is equal to integration probability of t given y multiplied by probability of y dy, right? This is, what is this distribution? Gaussian. Given y bar comma beta inverse in. What is this distribution? Again Gaussian. Y bar given 0 comma kn. So what will be p of t bar? Gaussian, by using the convolution property of Gaussian. And this is where we spent some time in the last lecture. So the overall thing is also Gaussian over t. Now what is the mean? 0, because y bar, I will take the mean of y bar, which is 0 from the A B formula that we did last time. 0. And what is the covariance? Kn plus beta inverse in. And we are going to call it as Cn. And Cn is now a function of beta and theta k, all the hyperparameters of my model. So Cn is now a function of all the hyperparameters of my model. All of these are unknown. How do we find out this hyperparameter? By maximizing this marginal likelihood. So theta, so training actually is theta star is equal to arg mean of theta minus log of Gaussian the negative log likelihood. We minimize the negative log likelihood of this of the data basically, right? To find out the hyperparameters theta. How many hyperparameters we have in the current setup? We have 3 hyperparameters. These 3 are the process variance sigma y square or beta inverse, which is the precision, length scale parameter L, and the process the noise variance sigma y square. So sigma y square and beta and L, or beta inverse sigma and L, I mean whatever you want to call it. So we have 3 parameters. Each of these have a meaning. Sigma y or beta inverse tell you about the noise in the data. Sigma, the process variance, tell you about how much is the variance in the predictions. L tells you about how correlated are 2 points based on the distance. So all of these are interpretable parameters. You can make sense out of these parameters. And this is what makes GP so elegant, because you are doing things analytically and you have a meaning of the hyperparameters you are training for. Unlike deep learning or neural network, where you have no meaning of the weights and biases that you are training for. That is what makes GP so special. It gives you good result. You can do things analytically, and you have meaning. The parameter, the hyperparameters in this case, have a meaning associated with it. You can make some sense out of it, and that's why it is so powerful. Okay. So anyways, this was nothing new. And when we open this log, and what do we get? We get this one, right? Theta star is equal to arg mean. I will get 3 terms, n by 2 log 2 pi, the useless term, useless because it is not a function of theta. So I will basically ignore it. Then you get half log determinant of Cn, useful term because Cn is there, Cn has theta, you cannot ignore this term, you have to work with this. And remember, last time I said that log determinant, you should not write your own code. There are efficient algorithms and codes inbuilt in MATLAB, Python for finding out log determinant, you should use those. Okay. And the last term is half Cn inverse T bar. Right. And this, how do you get it? Nothing. Just write the expression of Gaussian, take the log, and this is what we will get. Okay. 2 pi to the power minus n by 2, log of that, n by 2 log 2 pi. Determinant of Cn to the power minus half comes outside, log determinant. And log times exponential of minus half T transpose Cn inverse T. Take a log, exponential log cancels out. The inside term comes here. And this is where we stopped, right? Now we wrote that 2-line algorithm with this, we stopped. But this is not our end goal. What is our end goal? To make prediction. Our end goal is to make prediction. So how to predict using GP. Okay. So now we are starting new thing. So now how to predict using GP? Can you remind me, in a Bayesian setting, what does prediction means? What do you want to compute in prediction in a Bayesian setting? Predictive posterior or posterior predictive. What does it look like? Probability of y star given x star, comma d, the training data. This is what we want to compute. We want to compute probability of y star given x star, comma d, and this d is basically x comma y. This is what we want to compute, right? We discussed it earlier, that what does prediction means. In the GP setting, what will this look like? In the GP setting, this will be equivalent to, I want to compute probability of t n plus 1, that means the next prediction. It's not a time sequence, but you can imagine that I have n data, now I want to predict the next point. That next point need not be extrapolation, it might be somewhere in between also. Given t 1 to n. Obviously, x will also be there, x star and all those things. I'm not writing those because this is what I will work with. Okay. I mean, I can always write comma x 1 to n comma x star. This is correct, but I am not writing this to make it shorter. I'm not writing this because I will not operate on those two terms. So that's why in a shorthand kind of notation, I am ignoring those two. They are there. Don't assume that those are not there. Those terms are there, but as a shorthand notation, we will not operate on those, so I am ignoring those. X star and x1 to n, right? X1 to n is the training inputs. X star is the point at which you want to predict next. So prediction input, I will say, okay, or test input. Okay. Similarly, Tn plus 1 you can write as T star. Tn plus 1 is nothing but T star. I'm not writing it, but that's what it means. So we basically want to find it out, right? Now, keep this in mind, we'll come back to this. So now, can you tell me, or will you agree with me if I say that probability of T, or rather I will not write probability of T, let's say T. If I write T is a Gaussian process, will you agree with me? Now something new, let's see. Will you agree with me if I say T is a Gaussian process? Not vector T, the function T I'm talking about. Will you agree? And if you agree, why do you agree? If you do not agree, why do you don't agree? Is T a Gaussian process? But that does not mean that T will also be a Gaussian process. T can be some process, but we cannot guarantee it will be a Gaussian process. So first question is, you agree that T will be a process, right? A random process. The question is whether T will be a Gaussian process or not. Correct? What is a Gaussian process? Remind me about the definition of Gaussian process. It's a collection of random variable, potentially infinite, any finite number of which will have a consistent Gaussian distribution. So if I can show that a finite number of T has a consistent Gaussian distribution, can I not claim that then T is a Gaussian process? Can I not go the reverse route, where I show that, okay, T1 to n has a consistent Gaussian distribution, and therefore T is a Gaussian process? Will you agree if I can show that? So what is probability of T vector? We have derived it already. It's a Gaussian, not only just any Gaussian, it's a consistent Gaussian. There is a Cn sitting there, right? So there is a correlation structure in the T. You can see that 1 to n at least. So from here, I can extrapolate that instead of n points, if I had n plus 1 data point, training data, then this should have been Cn plus 1. If I had 2n training data points, then this should have been C2n. The structure would not change. It's having a consistent pattern. So from here, I should be able to conclude that T is a Gaussian process. A Gaussian process with mean 0, mean function 0, and covariance Cn, right? So T is a Gaussian process. Let's write with 0 and Cn plus 1. I should not write n plus 1, sorry. I should write only C. Why should I not write Cn plus 1? Exactly, it's a kernel. I will write n plus 1 next step. When I say that, when I write something, I'll see, you will see, I'll write it. This is fine. Now, if T is a Gaussian process, then from here, what is probability of T 1 to n, comma, joint distribution T n plus 1? What will it be? Multivariate Gaussian, right? Multivariate Gaussian, again from the definition of Gaussian process. Now the forward direction. Because T is a Gaussian process, any number of sample I draw from it will be a joint Gaussian. Gaussian process is a potentially infinite collection of random variables, any finite number of which, that finite number can be n plus 1, can be 2n, follows a consistent Gaussian distribution. So T1 to n, Tn plus 1 will be Gaussian. So this will be equal to Gaussian of t 1 to n plus 1, I am writing it together to save space, but it is actually same thing, right? T1 to n comma Tn plus 1, same thing. What will be the mean? 0. What? And how many elements? N plus 1. What is the covariance? Cn plus 1. Okay. Okay. Clear? Any question on this one? Any doubt that the joint distribution will be Gaussian? The joint distribution is Gaussian because T is a Gaussian process. T is a Gaussian process because the samples we had has a consistent Gaussian distribution. It is also a Gaussian process, as I earlier said, because Y is a Gaussian process and it's a linear relation. So linear combination of Gaussian process remains a Gaussian process, property of Gaussian distribution. That also holds, I did not mention it, but that is also true. So any doubt on the fact that this joint distribution will be Gaussian? Is it clear that this joint distribution will be Gaussian? Because if this is clear, after this it is just algebraic manipulation. There is nothing conceptual as such after this. It will be some algebraic manipulation, because what we want to compute, remind me, it's written although, what do we want to compute? Probability of Tn plus 1 given T1 to n. So I know the joint distribution, I want to compute the conditional distribution. The joint distribution is Gaussian, the conditional distribution will be Gaussian. You will get a closed form solution. Not only that, the marginal is also Gaussian. I will not use that, but marginal will also be Gaussian, we know that. So because the joint distribution is Gaussian, the conditional is also going to be Gaussian, and we are going to use that at some point. Okay. Okay. So this one is from here we want to compute probability of T n plus 1 given T 1 to n. This is to be computed, right? Okay. We will make our life a little simpler. I hate this n1 to n plus 1. So let's call it A. Okay. T1 to n, let's call it variable A. This, let us call it variable B. So then I want to compute probability of B given A. Okay. So probability of A comma B is a Gaussian of A comma B with mean 0 and covariance, some name I have to give. I will not work with covariance, that will make my life difficult because I have to invert that, and a generic matrix I will not be able to invert. So I will work with what? Precision. What is precision? Inversion of the covariance matrix. So I will work with precision. What is precision? Lambda. Okay. Lambda is the precision in Gaussian case. Again, I will remind you that inverse of covariance is not always precision, but for Gaussian distribution, inverse of covariance is precision. For students T, it has some other form. Okay. So that is just an example, but for Gaussian, the inversion of the covariance matrix is your precision. Okay. Yes, I mean, you are correct. I mean, in the notation wise, it should be lambda inverse, but in the expression, it will only be lambda. Okay. And this is proportional to exponential of minus half A B transpose. So I am just writing as a row vector. Then there is this lambda. Lambda, will you agree if I write lambda in this form? Let's say lambda A, lambda AB, lambda AB transpose, so BA, lambda BB. This is fine. I'm writing it as a block matrix, assuming A and B are both vectors. If I am only predicting Tn plus 1, then a block matrix, 2 vectors and a scalar, it will be. Right? Fine. So now, what do you want to compute? Probability of B given A. Right? How will you compute it? Probability of B given A will be computed, and this is a very easy thing. You basically rearrange whatever is inside the exponential to retain only the terms having B. And whatever is not having, or whatever is not a function of B is to be treated as a constant. And this is known as completing D square. Because there is a square sitting inside the exponential, so it should be that the square terms should be together, the linear terms should be together, and whatever is not a function of B should be a constant. Okay, so that is what we will do. So this is equal to exponential. The first term, what am I interested in? Square of what? B, because we are interested in B given A. So we are interested in the square term involving B. What is the square term involving B? B transpose lambda B, B, B. That is the only term that has square in B. B transpose lambda B, B multiplied by B. That is the only term that is square. So minus half B transpose lambda B, B, B. Is there any other term that is square in B? You cannot have. Now we are interested in the linear terms of B. What are the linear terms? I will have two terms, right? One is A transpose lambda A B B plus B transpose lambda B A, right? So minus half A transpose lambda A B B minus half B transpose lambda B A. Okay. Now what is lambda AB and lambda BA? What is the relation between those? One is a transpose of other, right? So can I not switch A and B transpose and make lambda AB as BA transpose? What I mean is that, can I not write this term as B transpose lambda BA A? I can, right? And if I write it like this, the two terms becomes same. Okay. Minus, there is one more term which I will not write, so that's a constant. And when I mean by constant, it means it's not a function of B. When I say constant, it literally means it's not a function of B, because A is still, I mean, it's a function of A. But when I say constant, it means it's not a function of B. This is fine. One more line I will write, which is that combining the two terms in the middle. So exponential of minus half B transpose lambda B B B, this is my quadratic term, minus, now there are two halves, so it will become 1. So minus B transpose lambda B A. Right? Simple, right? Simple manipulation. Now what we will do is that we are here. So now we are going to assume or take a generic B given A distribution of Gaussian and take a similarity. And from the similarity, we will try to find out what is BB, what is BA. Because BB, BA, these are known to you, but the actual mean and covariance is not known to me. So what we will do is that now consider. So that was like equation 1. We will come back to that. So now let us consider probability of B given A. This is what we are interested in. And from the convolution property, from the Gaussian property, we know it is a Gaussian. So Gaussian of B given, it will have some mean. The mean will be, let us write mu of B given A, and it will have some precision. Right? and this mu b given a and lambda b given a are the unknowns. This is what we want to find out. This is proportional to exponential of, tell me what is inside, minus half b minus mu transpose b minus transpose lambda b given a b minus mu b given a, right? I'll again do the same operation as before. Open the bracket, keep this square term together, linear term together, everything else is constant. Same operation. So this is proportional to, I will not write the constant term. So half. What is the square term? B transpose lambda b given a b, right? What is the linear term? Tell me. Now there will be a plus sign coming into picture, you can understand. The linear term will be, I am combining the two linear terms. So it will be B transpose lambda b given a mu b given a, right? Anything else? B transpose lambda b given a mu b given a. The other thing will be mu b a transpose lambda b given a times b, but you just switch it, it will become the same thing, and that's why that the half is missing. Both are negative terms, so this becomes negative of negative becomes positive. Okay, so the sign is positive because it was minus, and the half is missing because two similar terms will come. I have added them. Plus constant is there, I am not writing. Okay, clear? So what have we done till now? See, I took the joint distribution which came out to be Gaussian because we are dealing with a Gaussian process. Y is Gaussian process, T is Gaussian process, because it is everything is Gaussian process. When you take that joint, it becomes Gaussian distribution. Now, from the joint distribution, we wrote down the joint distribution, specifically the exponential part, and rearranged it so that it becomes only a function of b. And we stopped there. Then we said that we know that the conditional will be Gaussian. So let us write it down. And then we again opened the bracket and wrote it in a form so that I am now in a position to compare the two. So I am now going to compare this expression with this expression. Okay, I am going to compare the two things. So if I compare the two things, so let's call it equation 2. This is 1. So comparing 1 and 2, from 1 and 2. Can you tell me what is lambda b given a? What is lambda b given a? Just by comparing. Lambda bb. Is lambda bb known to you? Is lambda bb known to you or is it unknown? What is lambda bb? This one. How do you get this lambda bb? By inverting Cn plus 1. Right? Is Cn plus 1 known to you? It is, because theta you have already found out. By training, by maximizing the marginal likelihood, theta you have already found out. So C is function of what? X. You know the x and the point where you want to predict. And theta. Theta you found out by training. What is unknown in Cn plus 1? Nothing. So Cn plus 1 is known to you now. And that is what the purpose of training is. To find out the unknowns. The only unknown in C was theta. Theta I have found out now. Because I have found out theta, that means Cn plus 1 is known to me, which means inversion of Cn plus 1 is also known to me, which is lambda. Right? So that means if lambda is known to me, that means lambda A is known to me, lambda AB is known to me, lambda BA is known to me, lambda BB is known to me, right? So if lambda BB is known to me, lambda B given A was unknown to me. So now it's known to me. Is it clear? Why is it known to you? Cn plus 1 is known to you because theta you have found out. Yes, you have some question? Where are you considering that? No, we are not comparing A comma B with this. I said you can find out probability of B given A from probability of A comma B by rearranging it such a way so that you can only concentrate on the B terms. That's what I'm saying. Which means it is all the terms that are A are not function of B. That's all I'm saying. It is same. It is not proportional. That's how you derive it. That's the derivation step. There is no assumption here. From any joint distribution, how do you find out the marginal conditional distribution? There are two ways. One is you find out the marginal distribution and divide by it. That is the difficult way. You will not be able to do that integration. Because the other way is that you take the joint distribution and rearrange the terms and then look at the terms which are relevant to you. These are two ways. One is known as completing the square, the other is known as going by Bayes' law. And these are the two ways how you can find marginal distribution or conditional distribution in this case from the, mostly conditional distribution from the joint distribution. Okay. So this is fine, but this is not enough. Mu B given A should also be known to you. So let us compare the second term. What is the second comparison? What does it give me? Lambda B given A multiplied by mu B given A is equal to minus lambda BA multiplied by A, right? Which means mu B given A is equal to minus lambda B given A. What is it? What is it? Lambda BB. So minus lambda BB inverse. Lambda BA. Remember, I was always saying that when you are predicting, you will not get a zero mean Gaussian process. See, it is not a zero mean Gaussian process. It has a mean, and the covariance kernel is giving you the mean along with the observation points, because A, it's also a function of A, right? And A is nothing but your T1 to N. That's what A is, right? So if I have to write it in our form, what will I get? Probability of T n plus 1 given T 1 to n is a Gaussian, right, over T n plus 1 given the mean term you care about. What is the mean term? Here it is, minus lambda BB inverse lambda BA multiplied by A. Now A is what? T1 to N, comma, the covariance. The covariance is lambda BB. This is your predictive distribution. So when you have to predict at a new point, this is what you will do. Okay. I'll write down the algorithm, but first let us go into Cn plus 1. What is the form of Cn plus 1? Let us spend 5 minutes on that, because Cn plus 1 will govern your lambda, and then we'll go into the prediction part. And the algorithm part. Prediction we have already done.
Cn term will also be there
in the outside, right? Yeah, that will also get arranged and go out. This outside term cannot go inside the exponential. So it's enough to only compare the term inside the exponential. Whatever is outside, it will get B and A. Whatever is the A is constant, that will normalize out. Okay, I understand there's a Cn term outside, but when you are comparing to Gaussian, it suffices to only compare the exponential term, because whatever is outside cannot go inside exponential. So that's why. Okay. Okay. Any doubt on this till now? Any question? Little bit of maths, you have to do it yourself to follow it actually, which I will kind of force you to do by in homework 4. Homework 5 will be released in maybe by this week. There will be 3 questions that I've asked. So there will be 3 questions in homework 5. Homework 4 will release maybe next week or the week after that. The reason is that Gaussian process, the last homework was until what point? Sampling and response service was there? It was there, right? CC was also there. That means the only thing we have covered after the last homework is Gaussian process. So let me cover some more topic that I can give you homework after that. So that's why I'm postponing or delaying that homework 4. Homework 5 I am giving because that I do not care. That's the bonus homework. So that will have questions that I will cover maybe in November. Also that will have questions that I've covered in July maybe. So that will have everything. That's a bonus one. So bonus one I'll release now. And you will have maybe 1 month time, maybe little more than 1 month. Probably I'll put the date after your measures for that, for the bonus one. Homework 4 will be the usual one. It will have 2 weeks time and whatever, but that I will delay by 1 week or 2 weeks, so that I can give you a homework that covers majority of the topics that are there in the syllabus for the majors. Otherwise, in minor it happened, right? The sampling question, I did not give you a homework for sampling, and you saw that it creates some problem, right? I mean, without doing homework, you will probably not be able to solve even the easier problem. The sampling was the easy problem. So that's what I'm trying. Even then it will happen. I mean, what I will cover on 12 or 13, there cannot be a homework for that. So that part I'll rely that you will do from some book, some problem on your own. Obviously, homework 5 will probably have that, right? But yeah, so still it will be there, but I want to minimize that portion, that for which homework has not been provided. Okay. Okay. So this is the thing. Cn plus 1. Let us focus on Cn plus 1. What is Cn plus 1? Can you tell me? It's the covariance matrix, you know that. But covariance matrix between what? What is this n and what is this n plus 1? What is this? It's covariance between the training data and test data and all of those, right? That's why you are getting n plus 1. Because your training data set is n. Prediction is 1. N plus 1 because you are considering both. So if you think carefully, and this is very easy actually, this one should be Cn, this will be K, this will be K transpose, and this will be a small c. Sometimes we write C star also. C star, or sometimes you write it K star. What is Cn? Covariance between xi and xj semicolon theta k plus beta inverse in, I mean beta inverse, let's say, and then I and j goes from 1 to n. I mean, this is Cn ij actually. Cn I j, right? This is your Cn. What is k? First of all, what is the dimension of k? Small k. No. It's n cross n. With n cross n, it cannot be a 1. It will not be constant. It is n cross 1. K is n cross 1. K transpose is 1 cross n. K star or C star is 1. So what do you think is K? Is the correlation between your input at which you want to predict with the training input. So K is, this is capital K by the way, the kernel, right? Capital K xi comma x star semicolon theta k. where I goes from 1 to n. So it gives you a n cross 1. What is K transpose? You can imagine is the transpose of that. I'm not writing that. What is K star or C star? It is K of x star comma x star semicolon theta k. Is it fine? Yeah, I was expecting that question. Why is beta inverse not there? I was expecting someone will ask me, where is the beta inverse? At least in this term, right? What is the source of beta inverse? Measurement noise. At x star, you do not have a measurement, so the measurement noise is absent. Okay, so that's why the beta inverse is not there. This is a very common question, obvious question, right? Where did beta inverse go? But that is why after writing C star, I said oblique K star. So that K means beta is missing. C means the beta is there. That will clarify it. But people also write C star. Okay. But beta is not there because beta is the measurement noise. You do not have a measurement at the new point. So where is the measurement noise coming? So that's why it is not there. Okay. And that is why you should also keep in mind I am writing Tn plus 1, but it is actually Yn plus 1. You don't want to noise, right? You don't want to predict the noise. You want to predict the actual function y. So that is being catered by not including that. So this is how Cn plus 1 look like. One small thing I am skipping, I might cover it next lecture, I might not, is the relation between C and lambda. There is a closed form relation that you can find out. Okay. That's in the slide, but the derivation is not in the slide. I might cover it next time. Okay. I do not have time. I think the writing the algorithm is more important than that derivation. Okay. That's a small derivation, but you need to know Woodbury matrix inversion identity. Read about it. Woodbury matrix inversion lemma actually. Okay. The other one is SUR, S-C-H-U-R, SUR or SUR, whatever you pronounce it. SUR matrix inversion. So these two theorems will be needed to prove that, but you will need both of these. Woodbury matrix inversion identity and the SUR representation or SUR inversion. Okay. Algorithm. To conclude the GP part, what are my inputs? Now tell me. We are going to write the training and inference together, or training and prediction together. What are the inputs? First is training sample. So D, which is x1, xi, ti, I1 to n. Then choice of your covariance kernel k. Then I am writing the total algorithm. So prediction is also so x star. Right? Step 1, you calculate the loss function. So, or directly write, let me write directly, theta star is equal to arg mean theta 1 by 2 log determinant Cn, which is a function of theta, something like that. Again, I should not write like that. How should I write it? Okay, you keep in mind that Cn is a function. This representation is for kernel, not for matrix. So Cn, which is a function of theta, let me write it like this. This is better. Plus half t, you have this t here, so that's not a problem. Transpose Cn theta inverse t. Right? To find out the parameters like this. Then formulate Cn plus 1, and you can do that because x star and x are both known to you, theta is now known to you, so Cn plus 1 is not a challenge any longer, which is basically Cn k, k transpose k star. Okay, and then from there you will find out mu, which is the predictive mean. So mu Tn plus 1 given T1 to n, something like that. which is equal to, what was the formula? I forgot. Here, minus lambda BB transpose lambda BA or that was not by, it was, I can sometime write C star, sometime write K star. So that was the two representations I used. Okay, it's good that I changed it so that that confusion got away. Multiplied by T 1 to n, right? This is okay, which is also equal to, now I'm giving you the final form, which prove I have not shown you, K transpose Cn inverse T 1 to n. So this is equal to this. I have not proven this. 1 by n, n by 1, all those things, right? It will come because of that. Okay. So this will be the your mean. This derivation from lambda to c I have not done. I might do it next time, or otherwise I told you that using those two theorems you can do it. It is a half page kind of theorem. I have proved not that much. Okay. What is the variance? Sigma T n plus 1 given T 1 to n is equal to what, lambda BB, I think? Lambda BB, right? Which is actually equal to, I hope I am writing it correctly. Let's see, K star minus K transpose C n inverse K. Okay. Again, this proof I have not shown, but this is what you will get. Now, how do I know this is? How do I check whether it is correct or not? Look at a dimension. I know lambda BB should be a 1 because T1 n plus 1. K star is 1. K transpose is 1 cross n. N cross n, n cross 1, I will get 1 cross 1 dimensional matching. So 99.99% this is correct. Okay. The confusion that I have and you might have is that which inversion will go before and which one will be first. So that you can verify by looking at the dimension. Okay. Similarly, in this one, K transpose is 1 cross n, then n cross n, then n cross 1. So you get a 1 cross 1, and it's supposed to be 1 cross 1 because it's a predictive mean, a scalar in this case. Okay. And that's it. This is your algorithm. 5 lectures we spent for these 4 lines. Okay. So return mu comma sigma. I mean, sigma means this one. I'm not writing a total thing, and mu means that. So ultimately, your GP will come down to 4 lines, assuming you are using a good optimizer. So one of the initial thing I did not write is that you should also give me some initial value of theta, because you will solve it iteratively, right? So some initial guess of theta will also be needed, which I have not mentioned. Okay. So this is all about Gaussian process. The idea is very simple. You want to use Gaussian process to make predictions. To do that, you assume your prior to be Gaussian process, do the maths, find out your posterior as a Gaussian process, posterior predictive as a Gaussian process, and from there you get a Gaussian predictive distribution. And I have done it for T n plus 1. You can imagine that can be T n plus 1 to n plus k. It still holds. Whatever is 1 will become k cross k, and you will get k outputs. The mean will become k cross 1, the covariance will become k cross k. So it can be a multi-output GP as well. I mean, nothing changes. The formulation holds for both. I showed only for univariate case, right? Okay. So this is GP. This is what you will need actually practically. Whatever is before that is all derivation, which is needed to actually fully appreciate what is happening here, right? To fully appreciate this loss function, right? You need to understand what is the likelihood, what is the marginal likelihood, what is the negative log likelihood, and from there you arrive at this. Directly looking at this will give you no sense what is happening, right? And same for anything else. Okay. Any question? How?
This CN plus one matrix came up.
How this came up? Very good. How CN came up? How Kn came up? Let's start with Kn. From the kernel, right? Kernel. So what was Cn? C1 was also kernel actually. C is what? Is a kernel. Original kernel plus some noise. That's the K, C. So C is a kernel. So from that kernel you get this. There is nothing new here, right? This is the, instead of n training data, you have n plus 1 training data. Then this will be your training kernel. There is nothing there. Okay. The only thing that has changed, there is only one change. The prediction point, the noise is 0. Because there is no prediction, no measurement, so no noise. That's the only change. Other than that, it's exactly same as what you had for the training data. Okay. So you will have to do these derivations to fully appreciate it, because see, when I cover it in probabilistic machine learning, I first take 5 lectures on probability and statistics, then another 10 lectures on Bayesian linear regression, then sampling, then comes this. By the time I come at this, you have already done the Bayesian linear regression and all those things, so you are more familiar with the sum law, product law, their application. In this course, I did not have that luxury to go into Bayesian linear regression. I could not. So what I did was I directly go into Gaussian process and then took diversions. Now, these diversions are never preferable. So as a result, you have to go do this derivation at least once to fully appreciate certain aspects of this. Okay. And once you do it, you will realize it's not that difficult. Actually. The most difficult part is what I skipped actually, which is this derivation, because that's a half page kind of derivation. The mean one is like 2 line. The covariance one is like half page. Okay. So I'll probably do it next time. Let's see. Okay. Depends on how much surrogate modeling conclusion time will need it. I'll need 15 minutes for that. So if I have 15 minutes, I'll do this. Okay. It's not that difficult, but the other parts were even simpler. That's what I meant. Okay. Okay. Thank you.